Okay. I hand over to Joost for part two of his he can explain to us about the rings from the
Fusion rings.
And you're going to want to.
Yes, that's right. All right, so for the benefit of everyone, probably I should just briefly recap what the fusion ring was, and then I'll try and talk about fusion categories afterwards and how they sort of, how fusion rings fit in there. But I will actually say very little about the actual or the category structure. It will all be there in on the board, but it's a bit like as if I'm talking about relativity by talking explicitly about the Aristotle symbols and mentioning the completely coordinate tree perspective. But in this case, I think it's actually easier. So anyway, first of all, let me remind you what the fusion ring was. So fusion ring, basically, you have this gadget which is about adding charges of some generalized notion of charge. So we have charges, set of charges, which we usually label A, B, C, etc. And it's usually considered finite. Although for many of the things we do that's not so important, but just make things easier. So one of the things we can keep in mind is as an example, which is better than an electric charge, is a spin. So then you have spin 0, spin 1/2, spin 1, etc. Of course, there are infinitely many spins, but we showed last week the way to cut it down to a finite number. So it's usually a good example to keep in mind. Many of the structures that I will talk about also exist for spins. And these charges can merge together, or at least if you have two of them sitting in your system, you can look at it from a distance and think, oh, overall the charge is something. So we indicate this fusion with a little cross and say A times B sum over some coefficients and ABC times C over all possible charges C here, where NABC is just some positive or non-negative integer coefficient. So in particular, all of these ends are 0, that means that A and B can also combine to C. If a lot of the other ends are probably 1, which means it's a unique way to combine A and B to C. So for example, if you have 2 spin 1/2, so combine to spin 1 in a unique way. And sometimes even greater. So for example, if you think about color, instead of spin and you have SU3, and then you have 2 8-dimensional 2 octuplets, you combine them together, you can make actually 2 different octuplets from those 2 octuplets. So then n should be 2. And of course, it's nice to think about this in terms of diagram like this, which at the moment don't mean very much, but it gives you the idea anyway. And then if you want to make this structure, these are called fusion rules. And of course, you can make this structure into a ring or even an algebra by saying, well, instead of just having these charges, I allow myself to have arbitrary linear superposition of these charges just formally. So I can say, oh, superpositions are allowed. Sum over C lambda C times C, where it's just a complex number here. It's lambda C. And then I have a multiplication of charges given by this cross, which we can just extend into linear combinations by making everything distributive. And it makes it into a ring with, in fact, an algebra are nice complex numbers. So we also have multiplication by scalars. And this algebra is, well, it doesn't have to be Abelian, for example, because I not required A times B times A. So, but the special thing about this algebra basically that this is based on charges where the structure coefficients are these non-negative integers. Yes.
These set of charges, they have to be finite if it was like a set of, let's say, continuous charges.
Yeah, so everything is easier to find out. In many cases where you're interested in topological properties of matter, for example, it's sort of also natural to think about the finite versus discrete set of charges, because if there's a continuum, I think maybe I can change the charge a little bit by this, doing something, changing some continuous parameter, and I don't really want that. But there's no real necessity at this level of description. So if you want, you can keep in mind that they're continuous. I actually know that makes sense. So, right. And there are a few other things that are required. It's an algebra, of course, because we require selectivity. So A times B times C is A times B times C. Practice like this. It just means that it makes sense to think about the algebra theory. Doesn't matter if I put the first together, but the last together. And we also have a trivial charge for the vacuum charge. So it's like the node charge. Often it's written bond. It's also a property that we require. That's 1 times A and A times 1 are both equal to A for all A. So if I add a trivial charge to some other charge, it's still the same charge, basically. And finally, we require that for every charge A, there is a dual charge, a bar, which may be the same as A, it's just that there is one, doesn't have to be a different one, such that if I take A times A bar, or a black A, so it has to be the same. Both of them will contain at least the identity part of the trivial one, and then maybe other attributions, maybe other charges that appear. But the important thing is that you can create or annihilate, if you like, together with the back. So that's the rest of what I said last time is homework example. And the story about how you can try to find more examples of these 5,000 different ones of them. So that's where we go. Any questions?
Since A times A bar, there can be many representations which include the identity. Is there a unique way of picking out A bar?
It's part of the action that there is a unique A bar. Yeah. Yeah. So as you can
so to understand that better, is the statement that A times C or C not equal to A bar never contains the identity.
Yeah, I think I wrote about it in A1
Yeah, in A B1 okay, that's really strong actions.
Yeah.
Because typically group representations satisfy all the other axioms except this.
Well, the fact that if you have the chart, you also have the inverse.
Representation also do this. So for every representation group, there is a unique representation.
But in the tensor product of representations, for instance, of SUN, there will be many the tensor product of 2 representations. Many will contain an identity. The tensor product.
Yes, but there is always the most one identity.
Sorry?
So if you take a tensor product of 2 representations, of, for example, a compact Lie group,
Yes.
there's always at most one identity that tensor product, or at most one trivial representation. And if I tell you that I have, for example, the 3-dimensional representation of SU3, and I go to tangent with something, it has to be 3 bars if I want to get the identity. There's always a unique one. And in fact, I can write down exactly what that representation is, because if I take a representation of a group, then so there will be some representation phi, which sends this into new ns. Right? Then if I define the transpose, if I define this representation, E goes to transpose in the transpose matrix. So I take the phi view first, and I take the transpose one, it's also a representation.
Yes.
And then which we call phi bar. And then I can show this as a unique representation such that phi bar equal to the identity representation plus other stuff.
Oh, yeah.
And there are no other representation.
Okay, excellent. And so the only difference in this case is that these are grounding axioms, but they're infinite dimensional.
Yeah, there are many of them usually. If it's a finite, then it's really satisfies it. Okay.
Sorry, I'm got confused, because to me, the conditions you wrote over there are exactly the conditions that you said had in modular, right?
It also includes groups directly, so if you say that there's only one compiler appearing on the right-hand side, not multiple, not the sum of them, but only one precisely, then it actually is a group. So it's two things multiplying by another thing, and they're associative, and you know, you have an inverse. So this was one of the examples of that. And but another example is take a group and look at the representations of these, the irreducible representations of that group. Then you can take tensor products of irreducible representations. And the tensor products can be decomposed into flat coordinate composition, essentially, like with SU. So you say I have 2 3-dimensional representations. They give me total. If I take the tensor product as a 9-dimensional representation, this decomposes into a 1-dimensional, 3-dimensional, 5-dimensional representation now. That's another example of this. So these are the 2 sort of extreme examples in some sense. Yeah. Good. So is everybody now comfortable more or less again with your work?
You need to tell explain people to people how to pin their people need to pin the speaker view
Okay.
to the lecture to the blackboard. If you right click on it, you will find pin, and if you pin the blackboard one, then it won't flicker around for you. Hopefully people are able to hear that. Yeah, I see that. I just muted anyone that wasn't.
Okay, so this is on a really abstract level where we were saying, well, there's these charges, there's labels, and but we want to now bring this a level closer to physics, and we want to say these charges are actually describing some system with multiple particles, and each particle can have one of these charges. And if we have multiple particles, then there are states of the system, and these states can have the different charges. So the naive thing is that we can say that these charges will be essentially detected by some operators acting on the system. So they're observables. And then the simplest thing is to say I put particle here, particle A. A particle doesn't have a charge yet, but there's an operator that surrounds the particle. And if I measure this operator, I find an eigenvalue, and then I declare, oh, this eigenvalue corresponds to the charge A. So that means this particle could have been labeled by A. It has a charge A in the first place, right? And then another particle over here might be labeled by B. But now I can also take an operator around both particles together. And this operator might find C. And then I say, oh, there's a state of the medium that has the 2 particles in it, where one of them has charge A, one of them has charge B, and the total charge is C. And I can imagine, for example, that this state might have formed by initially there was a charge C and then split up into charge A and charge B. Doesn't really matter, but I can imagine that there's some. This is another way of writing the same thing. So yes.
If 2 particles have the same charge, is there anything else that would break their charge degeneracy?
If they have the same charge, then essentially you would just end up with A and some overall charge C. Or is that what you mean?
Yeah, I just want to know, are you allowed to generate particles here?
Oh, you mean are there other labels beside these charges? Like, so in principle that would be allowed, but we're going to just discard that possibility for now, just to make it easier.
So you do allow for the generate particles with the same charge?
Oh, you can have as many particles with the same charge as you like, but what I'm saying is that we want to consider these charges to be the ones that are sort of interesting to us. There might be additional quantum numbers that distinguish the particle, but they're going to be completely irrelevant to physics, and we just ignore them. Basically, so this for now, this okay, and yeah. So now the idea is that instead of just having these charges, I'm going to say, well, there is going to be a set of states for a system with two particles, which they don't have to be actual fundamental particles. They can be quasi-particles in a system that consists of electrons, for example. But I'm able to fix these two particles in two places, and then I look at the states of the system in that configuration, and there's a finite number of states, and I can characterize them first of all by the global charge. So for every and in reality, this will be sort of minimal energy state or something. In reality, of course, I can always make lots of states, but I want to get down to finite set states of a system of two particles charges A and B, and I can label these with the total charge C. So that's already one way to take the two particle space and split it into subspaces. But I may still have multiple states at that point. So what happens is that then the dimension of the space where I have precisely that situation over there, charge A, charge B, and total charge C, is just NABC. So this is now the definition of NABC. We just say, oh, there's a physical system. We put two charges. We can detect that they're charge A and charge B. We can detect that the total charge is C. Now it counts the dimension of the Hilbert space, the dimension of the space of states with that property. This is some finite integer. And suddenly it makes sense that these NABCs are positive or non-negative integers, right? Okay. But once we take that point of view, then it makes sense that we also want to go beyond just describing the dimensions of the spaces. We actually want to describe the states themselves. We want to be able to say something useful about them, right? So once we do this now, we want to describe the states themselves. So for example, it makes sense to say, well, we know that there are an A, B, C, and D states, and there is going to be a basis for them. We don't know exactly how to distinguish them at the moment, but we just depict these as if A and B, they would use the C, and we introduce a new index, mu, which just labels a basis, which runs, so mu runs just 1 to N A B C. Right. Sorry. all of our states with two particles given that they have charges A and B and total charges C. Yes.
So I'm gonna ask my previous question again. Two particles with the same charge, are they allowed to occupy the same state?
I'm guessing I don't really understand the question. So when you say are they allowed to occupy the same state?
I mean, I'm thinking of like, are they bosonic-like or fermionic-like?
Ah, right. Okay. Yeah. So I'm not saying anything about that at the moment. So in fact, you could be completely. That's kind of a next level of description to say what happens when you exchange the particles. At the moment, these particles are all distinguishable because I'm actually saying where they are. So you know, like I don't have to worry about whether they can occupy the same state because they never do. But there is an important point, which is I'm not allowed to put two particles in the same position at all. Otherwise, all this stuff doesn't work. But that makes a lot of sense for quality particles in quantum symmetric systems anyway.
Yeah.
Yes. Good. Okay. Good. And then the next thing you want to say is, well, yes, well, that's nice if we can have a basis of states, but we also then want to see what physics does to these states. So what can we at the moment do? Well, we can, if the particles were, for example, sitting on a line, so here I drew this in 2 dimensions, which of course can also be in 1 dimension. And so then we just have particles A and B. And there will be some operator here that sees that this is A, and one over here that sees this is B, and one that is over both that sees that the total thing is C. So the minimum thing we should be able to do is look at histories of the system which are using and splitting the particles. So of course, a typical history could be we start with some particles A and B at time 0 here, and maybe there's another particle C, and A and B are going up. This is time here. And they fuse to a particle, let's call this one G, and then this one splits into C and D. And so it's this time here, you have particles C and G, or yeah, this could be C, the same C as that, right? It could be the same charge there, doesn't matter. And this one goes up here and it splits, and there was an H and a K here, but maybe they decide to come back together later. And then it's back to some charge F here. Now, of course, we probably want this charge F to be C, same as T, because otherwise this charge will not be conserved in this process. But okay, that's something that we just put in later, or put an extra condition. So now we would like to say, okay, well, here at time 0, we had some state with 3 particles. Then some process happened. This process will apply some time evolution operator to the system. It will be some linear operator. And then at the end, we have another state. And so, but we would like to be able to calculate what this operator goes from here to here. Okay. So it turns out that this is surprisingly easy, but before, or easy to characterize anyway. But before I do that, I want to say something now about categories before I get to say anything about categories, which is that. So what you can do now is you say, okay, well here, if I look at the time slice, then I just have a bunch of particles. And I can think of these bunches of particles. So just you have a bunch of marked points on the line here. I can think of them as the objects of a category. Then, so I have one at the bottom, one at the top here. Then I have these diagrams, you know, with fusing and splitting, however I want, that connect objects at the bottom to the object at the top. So I can think of them as morphisms of the category. Does everybody know what a category is? Okay. Well, then it's probably good that I don't say too much about it because let me say before anything, I looked up tensor categories on the internet to see, well, will I tell them actually what a tensor category is, right? And I found a nice introduction to tensor categories, starting from basically you don't know the categories. And by page 64, they had defined the tensor category. What we have here is actually a sort of nicer version of the tensor category, which requires a lot more structure. So that probably appeared by, I don't know where, but past page 100, I guess. So I'm not able to tell you everything. But the point about the category is it's something very simple, where you have a set of objects. So there could be, for example, sets or groups or linear spaces, vector spaces, or anything that is a mathematical object almost. And you have a set of morphisms, which are the typical things that you expect to go between those. So between sets, you have maps that send a point to another point in another set. Between linear spaces, you will have linear maps. Between groups, you have homomorphisms of groups. And so the whole point is that you have a set of objects. In this case, these are the objects. But also, so you can, in this case, they're just like a bunch of, if you take a line and put a bunch of points on it with labels from the group of from the charges, that's an object. And then you have a set of morphisms, and they're just anything that connects to objects. And then the important thing is that you can multiply morphisms. So for example, this morphism here, I could actually hack it in two like this. Then I see, oh, there's another object here. GHK. And then I have a morphism that goes from ABC to GHK, and another morphism that goes from GHK to CPT. And they glue together. So in this case, the multiplication of morphisms is just gluing them in a vertical direction. This multiplication. That's the standard part of the category. Now, what makes it the tensor category is that you can also do a sort of horizontal multiplication. So there's a second way of combining objects and morphisms, which acts more like a tensor product. So here what you see is that, well, the simplest object here would be just to have only A, right? But I can make more objects by just putting a B next to it, or then a C. So, and the same thing with morphism. So if I put a vertical line here, for example, so this is just a separating line, not an actual line in the diagram, right? Then I see that on the left I have the object A times B. So you can think of this as an A tensor B object and a C tensor D object here. But this whole thing gets tensored with the object C on the right hand side. So this is like a tensor structure of the category. And similarly, this morphism here, this gets combined with this morphism, which acts only on those objects over there that are the other tensor part of this particular morphism. So and if I want to tensor in another morphism, I just draw another vertical line and I draw another bunch of another object at the top and bottom and another morphism. And so this way I can sort of naturally describe mathematically how all the different possible histories of a system like this can be made together from elementary parts. So the elementary parts here are just the individual particles, and for the morphisms it would be take two and bring them together, or take one and split it. And all of the other things are just essentially just gluing those kind of things together, either horizontally or vertically. But that's why the category structure is very nice for it, because the tensor category structure already has those two ways of gluing, and then you just understand how those work on the elementary bits, and then your principle done. And then it needs a whole bunch more, how to say it, axioms, of course, to make sure that everything is consistent and everything works how we expect. But that's the basic idea. So now I'm going to, yes.
So what is the tensor category then? Is it a set of all these morphisms, or how do you categorize it? Is it both? The
So-
category of morphisms, the category of linear multiplication.
So a tensor, so a category is by sort of design a structure with very little attached to it. So in this case, the category itself is just, well, I told you that the set of all the objects is basically just puts A's, B's, and C's, etc. at the bottom. You may also allow yourself to make linear combinations of that, but let's not worry about it for now. And the set of morphisms is just all the possible ways to connect one object with another one by some diagram with fusions and splittings.
So would you call morphisms a separate tensor category or all of these?
No, so to have a category, you need to have objects and morphisms. So those are both, in order to call it a category, you have to have both those. That is a category. Now, what makes it a tensor category is that you can have this horizontal. So also to make the category, you have to be able to multiply the morphism. So the vertical thing is already there. And this multiplication has to also be associative and a bunch of stuff like, okay. And then in order to make a tensor category, you also have to be able to make this horizontal combination of things. And it has to happen both at the level of objects and at the level of morphisms, which sort of makes sense. And then of course those have to be consistent, so that if you combine two morphisms, then the objects at the beginning and part and end of the morphisms are also combined, etc. Yeah, so that's essentially what the structure is. But for my purposes, and then there's another important axiom which I'm not telling you, but I'm going to tell you in a minute very precisely what that is. And in my picture, it's called the Pentagon equation. It's essentially a generalization of this associativity at the level of states. Okay, so that's probably as much category theory as I can do that today, because otherwise I'll just spend the whole afternoon just talking about categories and you won't see anything about actual topological stuff. So, but feel free to ask. All right, so I talked about the two-particle space, right? So I have two-particle state, and okay, one more thing. So if I want to, I can think about this space also as the vector space generated by all the morphisms that go from C to A tensor B. So if I want, I can give it a categorical meaning that way. And I say, oh yes, it's Hilbert space is that. But for the physical point of view, it doesn't really matter. I can say I have two particles A and B. Let's use the C. I have a bunch of states for that that have those characteristics, and I label them 1, 2, and ABC. Okay. Now, what if I have three particles? Two particle states. So now I have A, B, and C. There, obviously, it makes sense to just try and label these states first of all by just the intermediate charges that I can get by bringing these together. So I say, oh, I bring A and B together, give me some charge B, and then I bring C together with E, and that gives me some overall charge D. And if I'm lucky, this is already enough to completely fix the state. There might be only one, but of course, in reality, if there's a high multiplicity, more than one for here or here, then I have to introduce some extra index mu. And mu, so this mu here would belong to 1 down to the end. Right. And this mu belongs from 1 to n of A or B. GD, yeah, precisely. So this tells me precisely how many of these states there should be. Maybe n A B times n BCD. And that's a set of three particle states. But obviously, and I've sort of almost completely fixed the basis for them as well, except for I didn't say what the phase of all these things. I can change them by phases. But of course, another natural basis, which is where I take A, B, C, and B and C together, these form some the channel F, and then of course I have to have the same total charge. And I might call this U prime. So it seems like there are two different possible bases. For the space. And then it makes sense that we should say, well, here these bases are not going to be the same states, because that would mean that the operator that measures this charge commutes with the operator that measures that charge. That won't necessarily be true. So there may be some non-trivial basis transformation, and let's just write that basis transformation as you can write explicit matrix elements. Well, first of all, A, B, C, and D are all fixed here, right? So we can rewrite A, B, C, D, E, U as the sum over F, U prime, and U prime. And then we write the explicit matrix element of F, A, B, C, D, and then E, S, U prime, times S, U prime, U prime. So you might say, well, why is that useful? But it's just explicitly saying that there should be these two bases are describing the same space of states, and so there must be a set of coefficients here. These are just numbers. This matrix is actually a unitary matrix if it's a proper basis transformation. I didn't tell you what the inner product was yet, but okay. So if I just knew these, that would probably help me in my description. And these are kind of these are kind of just saying what I had here, that the fusion order doesn't matter, but at the level of states. It's just associativity at the level of states. And if you do tensor categories, then there will be a structure called the associator in the category, which essentially is playing the role of these F symbols. This is called the F matrix. Notice that I don't see it. Okay. Yep. So
Just to see, in what sense is it a matrix?
it's just if you think of this state, this whole state is being labeled by E, mu, and U. So the outer labels are all fixed. They're just the global charge and the three particles that go in. And then I say, what is the space of states with three particles A, B, and C fusing to D? And yes, they're labeled by these three. But I think of them as one index together.
Yes.
Then also here, you think of these three as one index together. And then this F, A, B, C, D has precisely index 1, index 2, and it's an
I see it. Okay. So it's a matrix in terms of the three index.
So yeah, so these images are like normal images.
That's fine. Yeah.
But also, I'm going to now actually, for the rest of the talk, just assume that these ends are never bigger than 1. Just because then I can just drop all the Greek indices and it makes my life a little simpler. And it's also an important case. We see that a lot in actual physics. So from now on, I will just forget these. That's obviously. Yeah.
It's an obvious information. Just a collective index.
Yeah.
You can still call that E.
Yeah, definitely.
As a vector.
Yeah.
You said that it's unitary general, didn't you?
Yeah, so if we have to say what the inner product of these, but if we assume that all these states are normalized and orthogonal, which makes sense because we have some operators that measure, for example, E, then these are orthogonal based on eigenstates of those operators. And this is another orthogonal state because it's just the eigenstates of the operator that measure the charge of B and C together. So then we have a basic transformation between two orthonormal bases and automatically unitary. But mathematicians also study cases where F is not unitary, but for us, it makes sense to think it's unitary. In fact, there's also the inner product here. You need to know this, but if we take a state, for example, like this, then we think we should be able to take an inner product with another state, for example, one of these like this, where we can have a bubble here. And the way you can calculate it is by this taking the graph upside down and connecting it like this. Here. And then you calculate the amplitude for this diagram to be a single particle amplitude, and it's the space for a single particle is one-dimensional, so it's C. So this will just give you a complex number, and so that's a way to define the inner product. So that gives you a sort of natural inner product also in this space. It's right away. Now the next thing I want to do is I want to say, yeah.
This mu means coefficient of the NABC, and what is the set of the each of the NABC? This is the summation of C.
Yeah, so this mu can take this just labels the different states with A, B, and C, for which A and B can go to E. There are NABU those states. So then we just let this run from 1 to 2, 3, etc. to NABE. And we don't say exactly which states each of those is, but we just say there is a basis that runs that's labeled by some coefficient mu. Yeah.
So how do you determine the set each of the NABC?
This one?
Yeah.
So here you have this E and this C going together to D. And of course, this E isn't really a single particle, but we nevertheless assume that you can locally fuse these together. That's one of the things that is, of course, nicely organized in the category axioms that you can use. Similarly on this side, so here we have this mu prime going from 1 to N B C F, and this one mu going from 1 to N A F D.
So set is determined by the start point C for the CRE.
Sorry, I didn't get that.
How to determine the set?
So you have to ask again because I don't.
I don't know. So how to determine the set of this picture?
How to determine these, or how to determine this one? So I'm just saying this line is labeled E and this one is labeled C, and they go together to D.
Yeah. Okay.
So then we say, oh, we know how many ways there are to do that. It's C. And so in particular, in order for this to make any sense, we must have that NABE word. Let's say if you take NABE and NECE, and we sum of all the possibilities, this must be equal to sum of all for F N A F E and N E C F. But that's exactly the solution equation we had for the answer for. So it follows immediately from here, but Now we have more because we can actually write the actual states in this way. Right.
How do you know what type of diagram you can write down?
It's just physically inspired. So we just say physically we can move the particles around, and we can think of them as fused together or splitting, or they can actually fuse together and split. But yeah, of course, if we were in 2 dimensions, for example, then we could instead of splitting two, we could do something like this. We did one over here and that one goes behind it. And we actually can consider that, and that will be the next step, but we just don't do it for now yet. We look at the simplest case where we only fusion split. So only 1 dimension, that would be the only thing that can really do, because, and this is an assumption which we make the whole time, which I didn't really talk about. Is of course we could move this thing a bit differently, like this. But we assume that doesn't make any difference for the state, because it's topologically invariant theory where things only depend on the topology of the history of the details of how things move and stuff.
Can I ask a stupid question?
Yeah.
So isn't all of this information already in the group algebra?
So this is not in there. This is actually about the actual state, how this state relates to this state.
Oh.
So these F's are new. And now I want to say that these F's, you can't just choose them arbitrarily. There's a further restriction on them, which is actually quite hard to satisfy, and that's called the Pentagon equation. And only once you have that can you call it a fusion category or even a tensor category. And this is a very simple thing, which immediately comes up once you start thinking about 4 particles. So you can say, oh, what if I have 4 particles? Well, now I don't have 2 bases, but I have immediately 5. So I can say, oh, yeah, A, B, C, D fusing together to E. Like that. Where I say, oh, yeah, well, this fusion channel here is from A and B, and then I use C in there as well, then I have G, and then finally I use D. But of course, I have several different orders in which I can fuse them all together, so I can also take this one, where I fuse B and C together first. And then, so maybe I call this 8. And this is still G because it's global charge of the first two doesn't change, of course. And I already see that if I just focus on this part of the diagram here, that's just a 3-particle state. And I decided instead of A and B together, I put B and C together. So that's actually an F move. And that's the other side of the F move there. So here I can do this by applying F. A, B, C, D. A, B, C, G, sorry. There we go. So I can write this state explicitly in that way with F, A, B, C, G. Okay. But I have several other ones, so I could also go from here to here, for example. And these 2 are still together, but now these 2 are together first. So then I have A, B, C, D, E. These still go together to F. But now these go together to a new label that's called L. And F and L go to E. So this is another F move. But this is F C. So now I just move this one over there. So it's like I apply an F on these. So this would be an F of F C D and E. F C D. CDE, which is the other side of it. And then I have 2 more of these, so I can do another F move here, and then end up with this way. Where I just basically moved this B over to the right, so I do the F into this part of the diagram here. this will be F A B L and E. And finally, I could do a third F move. No, it's sorry, do here, I do one here. So we move this one over there, so we get this. I would still have H here, but this one okay now, and then this move here would be I see that I just did the F move here, so this one moved over there, so it was an F with A, H, D, and E with here. And then I could go from here to here by doing the F move there, where that C moves together with D. This would be an F of BCD K. And then I would end up here automatically with H and L. There you go. So we see that once I have 4 particles, I can already rearrange everything using the F moves that I have for 3 particles. That's a positive thing. I don't have to have special new moves for 4 particles, because I can just do local moves to 3 particles. But then I have different ways to do those local moves. One with 3 F moves and one with 2 F moves here. And they better give me the same results. Because if they don't give the same results, then it's inconsistent and everything breaks down. So, yeah.
The reason you don't let A and D go together and then B and C is because you're working one dimension.
Yeah, I'm not allowing them to go past each other at this point. So, yeah. But just wait another 20 minutes or something, or 10 minutes each. How far? Yeah, right. So I basically require that this is the same as this. And this is called the Pentagon equations for Pentagon equation, hopefully for very obvious reasons, because look at this, see that it's a Pentagon. And of course, here I just wrote in terms of matrices, but you have to be a little careful because the matrices don't always act on the same spaces. So if you write out explicitly all of the steps in this way, then you end up with a whole bunch of sums. And this is why I don't want to write all the Greek indices, because it becomes this really ugly, but you can do it. And then at the end you have
So can I may miss the point, but you are now giving an example of tensor category, and in this case, objects are given by each fusion ring, and morphisms are given by each F. Is this an example of tensor category?
so this is general. This is for you will have this structure in every tensor category. But for a particular tensor category, the objects are coming from some particular set of charges. So if you know a fusion ring, you can choose, you know, what set of objects are. So basically, in this case, you have one object here at the bottom, which is just E, and then you have an object at the top, which is tensor protocol for simple objects A, B, C, and D.
So does each diagram represent one fusion ring?
Each diagram represents one morphism in a fusion category. So this diagram is a morphism from the object B to the object A and B times 3 times D.
Okay, what's the F from the point of view of categories? What's the capital F?
The F is a natural transformation that
So is it different notion from morphism?
It's a different, that's not a morphism. It relates different morphisms. So you see that, no, actually, it's not saying that right. You have to functor, but
Okay. No, in this case, so A, B, C, D, E are objects of the categories, and each diagram represents a morphism.
and the F is the different F's are actually slightly different functors which relate different ways to make the tensor products. Like so, in principle, this one here we have the B and C tensor together first, and then the D, and then the A, because you see the B and C come together first, and then D and then A. And this F move brings you to a case where it's actually C and D come together first, still. Now C and D come together first, then B, and then A. And this F move is bringing you between these two different tensored objects, tensored morphisms and objects also.
It's the same pentagon that's cropped up in establishing associativity.
Yeah, it is the same pentagon as in conformal field theory would be like everywhere.
Or any time that you want to establish.
Yeah, that's true. Yeah. But I mean, if you want to describe it as part of the category structure, then you have to say something about in a tensor category, this tensor product here is actually this is a functor from the category times itself to the category, and then you can iterate that to have 3 copies of the category, 4 copies, and then those functors are related. So this is in principle comes from a different functor than that one because you did the tensors in a different order, and then the F is relating those different functors. So yeah. Anyway, like if I like I said, there are really good introductory text about this, but it gets a little hairy to explain it, and we don't need it. So as far as we're concerned, we can distinguish all these F's as this matrixes with complex coefficients, and it's equivalent to the category perspective. It's just saying in this category we choose a basis of simple objects and a basis of morphisms, which are these morphisms that go from one object to a tensor product of 2 simple objects, and then everything is related. Is described in terms of numbers, and matrices. It's like when you change from abstract linear transformations to matrices. But in this case, it's that's essentially what's happening. Yeah.
Are they always called Pentagon equations? I mean, I'm super 5 particles that you have.
Yes. So this is the next. So this is actually where one of the places where you want to import some knowledge from categories is that there's a nice theorem in category theory that called the Mclean Coherence theorem. Mclean Coherence, and it says essentially that if the pentagon holds, then you can keep doing these F moves for any number of particles, and there's no further consistency conditions that are independent. So this already implies all the consistency conditions that you would have for 5 particles or 6 particles or 7 particles, doesn't matter. It's automatically all works. So that's the non-trivial theorem, which was known in category theory since the 1950s or something. So 4 particle consistency or associativity at level states implies n particle.
So for the 3 particles, the
Sorry,
so 3 particle states, we also call them Pentagon.
so for 3 particle states, there is no consistency in a sense, because all of this saying that, well, this one is a bunch of coefficients like the time that one, it's almost trivial statement.
Yeah.
But then you have consistency conditions on the conditions, which come from when you look at more particles, you want to be able to do the moves on 3 particles at a time, 3 lines at a time. So you get one from 4 particles, that's the Pentagon equation. And if you go to 5 particles, you get a whole bunch of these equations, but they all imply that Pentagon equation.
Essentially, the bottom line is that once you have this, you don't need to worry about where you put brackets.
Yeah, exactly. This stop worrying and yeah, exactly. Yeah.
But did I pick it up correctly? The ends are not counted by the ends.
Not yet, no. I actually no. There are
ends the same set of ends.
yes. There are many examples of different ends for the
They're a
same.
new structure.
Yeah. But there is a theorem that says that if you give me a set of ends, there's only a finite number of different choices, or the different solutions to the equation, up to what's called gauge equivalence, which I can tell you about, depending how much time you want to still spend here. I will just to show you that this is not scary. I will just write the actual equation. In terms of the symbols, just ignoring the new, so all the ends are less than or equal to 1. Then it looks like F, C, D, E, and then we only have to worry GL here times F, A, B, L, E, F, K is equal to the sum over H of F, A, B, C, G, yeah. FH and FAHD, K, and X. KHL. So you will notice that all of the F's that I wrote here are in there, but now I wrote in explicitly what the indices are that are changing. So this, for example, the FFCE, that at the beginning was here, FFCE, and I see that here what I changed, so I changed this G to L there. So that's why it has GL. Then of course there should be a sum over L in principle, because in the definition there is sum over L. But because L also appears in the final state here, we can remove that sum because we can just declare that the component with this L, we just look at the component where this L is some particular value, so then we don't have to do the sum anymore, and compare that component along the other side, and we end up with only one sum over H, because that's an index that actually disappears. It appears here, and then it disappears in the final answer, so you can't remove it from the sum.
When you say n less than or equal to 1 means it's just 0 or 1.
Yeah, yeah. The multiplicity free is what we call that. Yeah. But you can still have multiple outcomes for fusion, just none of the outcomes more than once. Yeah.
The equation should look something very similar even for general.
Yeah, you can do it in general too. It's just it has a whole bunch of extra indices. Yeah,
Yeah, exactly.
Yeah.
Yeah. So if I draw a vector line on each of those indices.
Yeah.
The same. Okay.
It's perfectly fine. Okay, so now I want to say just a few things quickly about this, which I could, in principle, tell you something about why they are, but it would take probably a long time. But first of all, if you know all these epsilons, you can calculate all the amplitudes for all the possible fusion and splitting diagrams that occur. So, and so in fact, these epsilons totally determine your fusion category. If you go back and find out all the structures of the fusion category are, in the end, it's just the same thing as saying, give me all the F symbols. So given the F symbols, you can calculate all fusion and splitting diagrams. what do I mean with that? Well, okay, so if I have a diagram where I start with a bunch of particles at the bottom and I have a bunch of particles at the top, then obviously one way to one thing I can do is I can make some standard tree like this. Yeah, okay, B, C, B, E, A prime, B prime, C prime, and then label all these intermediate charges, you know, F1, F2, F3, etc., F4, F5. So, so these are like my standard diagrams, which only have trees and only in a particular way. And if I make a more complicated diagram, if I decided that, oh, instead of like this, we were going to bring these together first, and then they split up again in a whole bunch of new ones, and that one goes over there, and then that one goes over there, and this one maybe comes back together with that one, and maybe this one also split one off and it went there. The claim is that if I have a diagram like this, I can reduce it to a sum of diagram of these standard diagrams again. So, so essentially that means I have a standard basis for the space of states, actually in this case operators going from 5 particle to 3 particle space, and they're given by those trees, and any other thing that may happen I can immediately reduce to that basis times coefficients. And the way it works pretty simply, because first of all, if the thing was already a tree, then I can just use my F loops directly. So suppose that the tree was already a tree, like this, for example, these come together and then we go here. This is already a tree, there's no loops. So I can just use an F loop directly to move that one on there. Right? Just like I can just do an F move in this bit of the diagram and move this one directly over here, and that's no problem. So using F moves, I can always move the tree to the standard configuration where they're all coming from the right. If it's not a tree, so for example, I have some loop somewhere, like I had some loops in the picture before, but a loop that looks something like this. And then I say, oh yeah, well, I have a loop here. That's a bit of an issue, but for example, over here, I see that this was A, B, C, D, and E. I can just do an F move on this. F, A, B, C, D, F. So on the F. And then instead, it will now look like this, where that E has disappeared and F is sprouting off this loop. And then B and C are here. Still A, still D. Why is it interesting? So I just use my F move on this bit and it became that bit. Why is it interesting? Well, this thing had 1, 2, 3, 4, 5, 6, 7 lines of it. But this thing, I had these 2 lines have become only 1 line. So now it's only 6 lines. So I can keep that going and collect more and more lines off until in the end it just looks like this. And then I say, oh wait, but now I have a loop with just 1 line going in. That violates charge conservation unless this line here is a 1. Otherwise, this charge would just disappear. It's not allowed. So I'm able to say, oh, in the end, this line is going to be a 1. Then I just have this loop. In this loop, you can then make disappear for a number. It's a little. I'd say the simple loop is actually this. Actually, this 1 is like a bar here, right? And then according to this inner product over there, this is just the norm of this state. A bar coming from 1. But these states are supposed to be normalized, so therefore this is actually 1. So I can always remove loops like this.
So in fact, originally you did not have A with A bar with 1 possible or dot.
Yeah, but the point is
Why
that
is A with A bar not give a 1 and not give something else?
no, it doesn't have to, but the point is in this diagram, I already know that it gives one, and no line here. If it was going to give something else, it would be a line here. So I know in this case that they have total global charge 1, just because they appear in the diagram with no, but they appear from nothing. If you like, they must have global charge 1. Anyway, the main thing about this is that I don't want to make it plausible that any process, any physical process, you can just describe it completely with these F's. It takes a bit of work to really make this like a streamlined algorithm, but you definitely can. So these F's are the things you want to know, then you have the whole theory fixed.
So over here you had a C going to a C with a loop.
Yeah.
You're saying I can get rid of that loop.
This loop is of course not configured. This loop has an actual
There's a charge going in.
character into it, so this is necessary. But in this case, yeah, it looks like it would also.
It is an example of what you just got here.
Yeah.
So what does that want to hear now?
Yeah, so okay, if I want to describe the details, so then usually speaking, we think that this is actually just the same state as this thing without the loop. So you have to be a bit careful. But
I can do the move on halfway. I can do something. I can do that piece.
Oh yeah. You could take
So
this.
I get this.
This will have to be 1 afterwards.
Yes.
Then that means that now you'll have this.
Yes.
E and F will have to become the same, of course, otherwise you can't do that. And then so either it gives 0 is not equal to F.
Yes.
Or if is equal to F, then and you move this to F.
So
But in the meantime, we've done this F root to get here, and that F root will give you a contribution. It's not just 1.
that's fine.
And therefore the outcome of this inner product will not necessarily just be 1.
But I can float that F. It's going to be the F.
Yeah, precisely. So the inner will be equal to this F.
Okay, very good.
So you can calculate, like I said, all these things can just be calculated with F moves. So they all of these magnitudes are some combination of these F moves, basically.
If you come these lines into choose, then it's a little bit continuous.
Yeah, that's right. Yeah. And in fact, yeah, so in fact, in string theory, people do this, and then they say, we require actually that, so they say, oh yeah, there's it's called, they say, yeah, this would be a diagram like this, right? And then they say, well, this is actually just by deformation,
Yeah,
the same thing as
continuous deformation.
yeah. Same as the diagram that looks like this. Yeah, sorry for the terrible drawing in my ear. But they still say, oh, but in order to describe it, we changed kind of the asymptotic basis, and we have to rewrite the thing as a sum of a bunch of symbols times the other basis. It's still 2 different bases, and you still get that.
So it's exactly equivalent.
It's the same thing. A little bit more general, I think, because they actually work with conformal field theory, so infinite dimensional Hilbert spaces. But apart from that, it's the same.
I can also call it
Yeah, to do with scattering. Yeah. So a whole bunch of these ideas are in different places. Okay, so good. So maybe what I wanted to do, I'm taking longer than expected.
Was it that it is sort of activity of the underlying.
Yeah. In conformal field theory, this would be saying that operator algebra is associative. But in quantum metaphysics, there isn't really directly an operator algebra straight away, so you kind of have to. So yeah. But in conformal field theory, also you can usually forget a lot of the structure and just say, let's forget about the whole conformal tower and just think about the lowest rung of the tower, and then you degenerate to this topological structure I'm talking about. All right, so now the question is, how long should I continue to go? So I had a few things that I was hoping to do.
We have to sit it down next week.
yeah, but you actually have one, right? So yeah, precisely. So let me. Okay, first of all, because somebody already asked, I need to say that. So you can, of course, bring this to higher dimensions, particular to two-dimensional space, and then you can allow the particles to change. You can also go higher. Then we can look at exchanges, so that we have diagrams like this, and everything that can be built on them. So we have chart A, chart B, and chart C. For this one, we get A. We start with A here, like this. And so this would be a state which we would like to relate to the state where we didn't exchange them. So then we can introduce new symbols. This can also have a mu on it, of course, like before. And then we have some R, A, B, C, mu over mu, then A. These are called R symbols. And then these R symbols also must satisfy some consistency equations. Of course, again, you want to be able to apply them locally to any particular bit of a diagram. And these are called the hexagon equations. I'm not going to actually write the hexagon equations, but I'll tell you where it comes from. So the idea is that if you, this you might call braiding, if you're braiding the particles in the space-time, right? For fusion and braiding has to be compatible, which means that if I take a diagram like this, where I say, okay, well, I have two particles like this, and a third particle, and this particle is going to go over these two, like this. Well, this should give me the same answer as if I just decided to take this particle over the fused particles and like this, because this diagram could just be deformed into that diagram without any topological change in the history. These should just be equal, but then if I want to reduce both of these just to the standard basis, so I just want a bunch of F and R moves, and I reduce it back to replace it like this, and also here. Then I see that I need to use two different sequences of F and R moves on these two diagrams, and so they both have to be equal. So I end up with an equation that relates the F symbols and the R symbols. Actually, two equations, because I can do this with an overclocking or an underclocking. And so I end up with two sets of hexagon equations, because these equations have they look like hexagons. Okay. And then there's a further theorem which generalizes the Mclean coherence theorem, which is that you never have to go to more than three particles in this case. So here we define the R symbol with only two, the F symbols we have to define three, we just define only two. Then we go consistency with three from here, and then for four particles and five particles, it all already works because the Mclean coherence generalized theorem. Also, once I have that the R symbols, I can further simplify my life, even diagrams and braiding and everything. I can straight away bring back to some combination of F and R symbols. And it's actually not easy, not simple, it's difficult to see, because I look at some diagram, there's some complicated stuff outside, which I don't know what happens, but in this bit of the diagram, the particles are changing. A and B. then what I can always do is I can say, okay, well, let's just imagine that there was a 1 here. I can always insert a 1 wherever I like. Actually, let's imagine it like this. Then I can do an F move there. And okay, there's a subtlety that I should probably go like this and do the F move more easily. But okay. Do an F move. And then after that F move, it looks like this. This one, these two get squeezed together. And then I can do an arm move to remove this crinkle. And after that, this looks like that. Actually, this is an R inverse move, you can name it crinkle, but get the idea. So any crossing I see, you can immediately remove by introducing some more vertices, but then I have something no crossings and I can use F moves afterwards to bring that to standard form. Yes.
Why is the other crossing different from your?
So in 2 dimensions, it is literally because if you think about braiding strings,
Okay.
braiding over is different from braiding under. You can't continuously deform them into each other. In 3 dimensions or more, then actually these are the same. Because you have extra space and bring them through each other.
So is the difference there really where they're both over, and is both over equivalent to both under? Yeah, on either side of equality, they're both over.
Yeah,
I'm trying to figure out what the 2 are.
So the other arm would have.
Oh, it's only the left hand. One is over, one is under, and the left hand one. I see.
This would be the other Expo equation. Turns out they're independent.
But can you have one over and one under in the left hand side?
You could do that, but that doesn't give you a nice consistency, because if you do that, so this was over here, and so now you can't move this vertex past this braiding because it will get stuck. So it doesn't have a nice way of deforming it to something.
So
like
either
that.
everything's over or everything's under.
Yeah.
So when we were in the 1 dimension, why didn't we have the option of swapping the topological? Because
Say swapping, what do you
so like when we're going maybe over there, like we wouldn't A and C won't go together first and then B because they would go with each other, right?
Oh yeah, okay.
But what if I swapped A and B particles?
Yeah, I can do
And
that.
I don't necessarily have to go through a loop, maybe just have a tree diagram of A and B going to
Well,
B, and then
I mean,
keep
so
breaking
you're
it
basically
together.
saying I can make diagrams like this where I say it's so I have A, B, C, and then I say, okay, I have A which wants to go together with C, but then B just goes over to the left or something, and then it's comes together like this.
Well, what I'm saying is that can't you have a process that swaps A and B? And that could be A and B going together, leading to E, but then E decomposing into B and A.
Oh, you mean like A, B, E, E, A,
Now A and C could go together, right?
and C, yeah. Yeah, so this you can perfectly well do.
But then if I create the
In
loop.
this way, yes, if you want to go to US, yeah, but so this is something we could already calculate with this F moves. Because you can remove this bubble by the approach that is described.
Can't do it without creating a bubble top.
Yeah, that's it. Or we'll see. But then if you resolve this crossing in the way I just said, it creates a bubble. All right, so that's our moves. So we can now also do diagrams of particles exchange, right? And still all that then you have, if you go to the category picture, it's called now a braided tensor category. And it has an extra structure called braiding, and et cetera. But it all comes down to just knowing these R symbols. And then, well, if you allow me another few minutes, I'll say something about we actually, our own work more recently has been to try and solve these pentagon and hexagon equations. Just try and find the actual F and R symbols. This is not easy because, well, this is the hexagon. Here you have the pentagon equation. I won't even show you the hexagon, but it's something similar. That's a little easier actually, but okay. But you see it's a polynomial equation for these F symbols. So if you think of every one of these F symbols with particular choice of all of the indices is one variable, that means you have quite a lot of variables, especially if you have many different types of particles. And then these variables satisfy this third order polynomial equation. And there are a lot more equations than variables. So actually these are overdetermined. So naively speaking, you would not expect to find any solutions. But fortunately, we know many examples where there are solutions, and it's good. But solving them may seem at first hard.
Just, yeah. Last week you described the Ising fusion ring.
Yeah.
These ones are known presumably for the Ising.
Yeah. Actually, I will give them to you in a minute.
Okay.
So now, before I can give you the solution, I have to tell you something, which is that if you find a solution, then there are automatically always infinitely many solutions, but in a really boring way. And the reason is, when I put these three-particle space, when I make these three-particle spaces, or these two-particle spaces even, people call this gauge freedom. It has nothing to do with gauge groups or whatever, but it's just because it's a freedom that's sort of physically uninteresting. If I make my spaces like this here, A, B, and C, and U. So, okay, fine. I could have decided to change the basis in the two-particle space to some U, A, B, C, U, and then I have a U. So let's call this head, and this is the new head, ABC new. If there's some twiddle on it or something, or prime or whatever. So I can just change the basis. Everything will look the same as before, the prime basis. But the prime basis is, of course, from the matrix times the unprime basis.
Yeah, it's just a change of period.
Just change of basis. I can do this in every two-particle space. So that means that all of the equations that I have are just invariant under these changes. So that means that if I find a solution, I can do this change on the solution, and it will transform the F and R symbols. So, for example, an F symbol comes from relating. Let's not worry about the mu and u. So then these are just phase factors. So the mu and u are just only one, and this is just the phase factor. The u1 phase factor.
It seems like it goes there.
Yeah, I suppose, but it's physically not interesting because, in a sense, if I'm trying to find these F symbols, I don't care to find another set of F symbols that's related by a basis transformation. The same, yeah, the same thing. So, so if I look at the F symbol, I have A, B, C, D, E going to A, B, C, D, F here. Then I have this vertex here, means I can put a U, A, B, E on this here, ECD, so there's a U, ECD. And here I get a U, ECF, and a U from AFB. And this thing is equal to sum over F times this thing here. So if I do these changes with these U's, then it means that F prime of F A B C D by F prime would be just the roots rights U A F B U B C F over U And so I can do this transformation on the F symbols, and they will all still the new F symbols will still satisfy these equations. So that gives me a whole bunch of freedoms, one for each vertex. I can just do this. So on the one hand, it seems like bad news because I get lots of solutions, and how do I know which ones are different? But on the other hand, it's good because it means I can use this freedom to require the F stems on nice properties straight from the start. Then I lose some of this freedom, but I don't care. Actually, I would like to lose all this freedom. Then I will have a nice discrete set of solutions. In fact, there's a theorem of Newhamian rigidity. And this says, up to this freedom, this gauge freedom, like, we have a finite number of solutions. To the Pentagon for each given the fusion rules. So if somebody gives us the NABC, the actual fusion rules, then we can set up the Pentagon equation for them. And then there will be a finite number of solutions once you take out this freedom.
And that finite number of solutions should be distinct.
Then the different ones there are actually really distinct. Yeah. They're physically different theories which lead to different amplitudes, regardless whether you change the basis. Of course, a lot of the time the finite number can be zero. But also, unfortunately, we have many examples where it's not zero, and also many examples where it's not one, and more than one. So, for example, for the easy model where H two solutions for only the F systems. There's a similar theorem once you take also R symbols into account.
So you might not erasing the diagram at the very bottom left.
These ones?
Yeah, I'm going to have a question.
Okay, sure. Yeah, good. Okay, so
Those boards move as well. I think that's something behind them.
You can slide it.
You can slide it to the center.
Right.
oh, yes, you see. Okay. Ah.
Not all the way.
That's a huge.
Look at that. Okay, so yes, so taking that into account, now we can have a strategy for solving the Pentagon and hexagon equations, and the strategy is very simple. So there's an even simpler strategy. Which is to say, well, these equations are polynomial equations. There are standard solvers for polynomial equations, which are algorithmic, and will always, in principle, give you the solution. So you just put them in and you wait for the program to output the solution. Unfortunately, or fortunately for me, because I can do something interesting, these algorithms are extremely inefficient. So if you try any case here, you can just wait till the end of the universe and you will never get the solution. Okay, so you have to do something slightly cleverer. So the first thing you can do is try to exploit the gauge. So our first idea would be the fixed, and we focus on the Pentagon for now. I don't want to talk about Expo, but it's the same idea. So we fix as many symbols. Fix as many F symbols as possible to be equal to 1 by a gauge choice until you exhaust the gauge. So what I mean here, it's very simple. Have a gauge choice. This is how the gauge informations work, right? Now, suppose that, let's say we have this UABE here. Suppose this is the only place where UABE actually occurs in this equation. So some of these U's could be the same potentially, and some of the indices are the same. But let's say this is the only one. So in Ising model, this could be like U of sigma sigma 1, and there's no other U sigma sigma 1 here. Well, then it's very easy to make this F symbol prime here equal to 1. So just choose this U equal to the inverse of all the rest on the right hand side. And then we've removed that U from the equation because that one is now fixed. And then in all the other equations for gauging F symbols, we just, whenever we see that U, we input that this U is equal to the rest of this on the right hand side. The only problem we can run into is if this N happens to be 0, because then there's no way if this is 0, this is also going to be 0. No matter what we do, so we can't do anything with this U then. So actually,
But wasn't the U being marked 1 or something?
what do you mean?
It should be, I mean, you did change the basis, so you shouldn't change the length.
So the elements be easy to make.
Oh yeah. You're right. So in principle, if we want to retain unitarity of everything,
Yeah.
then we would have to know the length of the F, the size of the F, and then this U would become a phase factor. But actually, actually we did that in an earlier version of the solver, but it's actually easier to just not worry about unitarity, just require that it's invertible, and then later after you solve the equation, you bring it back into the
Okay, yeah, that's it.
yeah. So so then we can set the ring to run. Yeah, so I said the problem is that this F is 0, so actually we get kind of step 0. Figure out which F can be 0 and in which combinations. So this sounds which combinations of F. It sounds terrible, but somehow the structure of these equations normally actually allows you to systematically figure out which combinations of F can be 0. It's a sort of fairly horrible process, but totally algorithmic, you can figure it out. So we'll do that first. Fix the ones, the non-zero ones that we know are non-zero. You fix them to be equal to 1 as many as possible until you completely exhaust the gauge. So there we use the 1 gauge factor, but you keep going eventually use them all up. And then the next step is okay, now we've removed the gauge, so now we solve the equation without terms. Without terms. Now, what do I mean here? Look at this equation here. Actually, that's one equation. See, there's a sum there. So, but there are many cases, where this sum only has one term. Because it just this H has to occur as the fusion of B and C, A and H have to fuse to E, and B and C have the H and E have to fuse to K. So there's a lot of constraints on it. So very often there's only one term. And then it becomes a very simple equation. This says these two F is equal to these three F. And you can just say, oh, let's remove this F because it's equal to these three F divided by that one. And we already know which ones are 0 and which ones are not 0, so we don't have to worry about that anymore. So that's a very, very potent strategy to remove lots and lots and lots of variables. So when I say the sum, I just mean that's.
So if no F is 0, is it possible that the combination of F be 0? It's not possible, is it?
They're literally complex numbers, so if you take a product of them, if one of the things in there is 0, then of course you know that the whole product is 0.
Yeah.
But if they're all three non-zero, then it's still non-zero.
Oh, so no combinations could be.
Yeah, you can't get unexpected. You know exactly which one from both sides, which of them are 0. Yeah. So this you can just do by picking F symbols that are on their own on the equation and just setting them equal to the rest of the F symbols, substitute it back, and you keep going until we run out of that kind of equation. And then the next step is then solve the remaining. Now you only have equations with sums, but many of them are still linear in one of the F symbols. There's only an F symbol and that appears only once, not as a square or all this bit. So then we solve the linear equation, linear in at least one F symbol. So that's easy because we know how to solve linear equations in one variable. That F symbol becomes equal to the rest of the stuff. And substitute that back. And then finally, now you have a much more set of variables left and a much more number of equations if you manage to, eliminate the ones that you solved and a whole bunch of other ones that become trivial. And for now, you introduce your standards. So use standard methods for solving polynomial equations. Sometimes you can just do it by hand, but for example, there's a method called Grosvenor basis, which is a kind of generalization of Gaussian elimination for polynomial equations. But this is precisely the method I was talking about, that you have too many variables or too many equations, or equations of too high order or whatever. Then the work explodes, but because these other solutions, very often you can actually find solutions this way. So now I know this is very abstract, so if you give me a few minutes, like really this is going to be very short, I can actually show you an example on the board. I won't solve the whole equations, but to show you just enough to get an idea how this works. I have to warn you that this example is a little unfair because these particular theories that I can solve this way are particularly simple and well suited to this whole scheme of solution. But we can solve much more complicated things using a code that I've been developing together with my students. This one's good for doing a blackboard example. So remember last week I introduced the Tambari-Yamagami theories. So these were, we had some group G, which of course has elements, G, little h, etc. And then the fusion rules were just D times H is the group product, GH. But in addition to this, one extra particle, which you might call sigma. This is not from the group, and we get V times sigma is same as sigma times G with sigma. So all the group elements just give the same big elements back because it gives the big element, and sigma times sigma gives the sum of all the group elements. So, and a special case of this for G equals Z2, and this gives easing because then, the Z2 have elements, let's say, call them 1 and psi. Because the Z2 we have psi times psi equals 1. And then we have sigma times psi sigma. And sigma times 1 also, of course, and sigma times sigma. So if you've seen the using model before, you can now see that it's the same as this Tambari-Yamagami thing for Z2. Okay, so now we say, let's look at the F symbols. I'll just give you the solution first. That will fully help. So now F G1, G2, and G3. So in principle, an F symbol has a lot of coefficients on it, but I don't have to tell you all of them because if I tell you that I have G1, G2, and G3 here, this one is automatically G1 times G2, and this is G1, G2, G3. And also, if I go to the other side and connect this one here, then this is automatically G2, G3. So it's clear what all the other indices are. So I can just label the top three. So this is well, I'll just write it explicitly, just FG1, G2, G3, and then the total charges, that's the product of the three, and the intermediate charges are G1, 2, 3. These are all equal to 1. So it's the only solution here is all these equal to 1. It's disappointing, but that's where we are. So this is literally equal to this reconnecting this there without any interesting coefficients, but fine. Then we have F sigma sigma G1 G2 and F of G1 sigma sigma G2 and F is sigma G1 G2 sigma and F is G1 G2 sigma sigma. So all of these are we have two sigmas coming together, two sigmas and two G's, and the sigmas are next to each other. So here with sigma sigma G1. This is G2, and this one is picked because, well, it has to be G2, G1 inverse in order for that to go together with G1 and G2. So I don't have to say the middle. And all the other ones are similar. These are also one. They're also on board. And then now we get to the interesting ones. So we have F G1 sigma G2 sigma is F of sigma G1 sigma G2. So here we also have two sigmas, but they're separated by the G's. And these we can write this this is the metric by character. So literally this means just that first of all, the symmetric part means it's equal to chi of G2 G1. And the bi-character part means that chi of G1 G and H1 H2 here is chi of G of H 1 times chi of GH2. So it's a one-dimensional representation or character in the second element, in the second what's it called? Entry. Yeah. Yeah. No, but the same thing the first one, which also follows from here. So it's also kind of G1, G2, H, sorry, G1, H, and G2H. So, and it's actually very easy for finite groups to figure out what all the symmetric bi-characters are. So this is, I don't have to tell you exactly what they look like, but I could do it, like, doesn't matter. Okay, and then finally, the most interesting F symbol, if you like, is where we have sigmas all around. And then you have to say the intermediate indices are the G, so G1, G2. And this turns out to be plus or minus. So these are two different possible solutions, plus or minus. 1 over the square root of the number of elements of the group times same chi, but inverted. So this is the whole solution. So you might ask, how do we know this? The reason we know this is because in this case you can solve the equation by hand. And also the other thing is, you should notice that I gave you two solutions. I didn't give you two enormous families of solutions. So obviously I already fixed the gauge somehow. So these are the two solutions up to gauge, after a gauge fixing. So in this case, if I wanted to do a bit of a solution with the calculation, first of all, gauging. How does that work? Okay, so for example, look at f of G8 sigma. Automatically sigma here also. Then if I gauge transform that, I will get u G sigma to H sigma divided by u to H and H sigma times X GH sigma. So this is the transform symbol. That's the on symbol. And we see that something nice happens because these factors here we use for the vertices which are just GH, right? Or the only group elements on the vertex. They all appear here independently of all the other ones, these are all sigmas. So I can use these to make all of these symbols just equal to 1. So we use these. Set f H sigma equal to 1 for all the image. And of course, there's one equation that I give here. That's that one. So that's just accomplished by gauge. And then, of course, if I do any further calculations, the UGH is equal to well, the whole f H sigma times u sigma times u sigma times divided by UGH sigma. So I have to substitute that back into the other equations if I want to be careful. Then I can keep going. So I say, oh yeah, fine, but similarly, you can look at, for example, yeah, also, I don't have to worry about this symbol being 0. So if this symbol was 0, it would all break down. But in this case, I know that this is a one-dimensional matrix. And also, these matrices are basis transformations, so they're invertible. So there's no way that this is going to be 0. It's automatically not 0. So if you want to see what I mean by DH sigma, DH sigma, and it will go by its optimal to DH sigma. This is automatically sigma because you put the sigma, and this is also for sigma. So there's only one possibility for the label of both sides. It means it's the transformation has to be some number, and it's definitely not 0. So then similarly, I can set, I'm not going to go into detail now, but tau G tau E the one using gauging with the new tau sigma. So that's a different type of U. And you said this E is just a unit element that's only for this particular. And then similarly, I can set F of sigma sigma G equal to 1. using rule of sigma. And so I can use up all the different types of views and use them to make various different types of f equal to 1. So this happens to work out very nicely in this way. Okay, and then once I've done that, I already have a lot of these equations, but then I can start looking at the actual. Then I can start looking at the actual Pentagon equation. And I'll do one of them. So in this case,
I think it's probably okay because
yeah, you probably can't follow it anyway.
we get the I think we get the idea.
Yeah.
Oh
yeah. Okay. Well, it's only one line, so I'll show you anyway. So for the Pentagon, I can do the simplest. One of the simplest Pentagon equations here is f(v1) 2 sigma times f for v1 v3. Sorry, f(g1) 2 sigma is equal to f v1 v3 and f G1 times G3 sigma, and then G1 into G3 sigma. And so you see that this would be decided that we normally have a sum, but in this case it's precisely one of those equations where there is no sum, so there's only one way to do it. There's only one picture of value h. And we were already, the first thing we did here was to make all of the ones that have 2 g's on the left equal to 1. So actually, this is 1. G's and sigma. This is 1. This is 1. This is 1. So we conclude that this thing must be 1 for all V1, V2, and V3. That was the first line that we wrote here. That this thing was have to be 1 for all V1, V2, and V3. So now, if you work hard through all the possible versions of the for all the possible Pentagon equations, you will find all the solutions. And there's one more remark I would like to say, which is that okay, so these pi characters, they exist, of course, for all groups. There are pi characters, but this matrix here still has to be an invertible matrix, otherwise it's not a basis transformation. So this pi character has to have the property that it's also actually a different pi character for a different character for every value of g. So it's non-degenerate, we'll say. This is a non, and that's only possible if the group is abelian, because in abelian, so this is a matrix with dimensions size of the group times size of the group. You must have a different character for every row of this matrix, but for non-abelian groups, the number of characters is too small. For abelian groups, the number of characters is precisely equal to the number of elements of the group, but for non-abelian groups, the number of characters is too small. So therefore, you can't actually make an invertible matrix, and this whole thing does not work if the group is non-abelian. So we gave both the solutions in case the group is abelian, and we proved that it's impossible that the solution if the group is non-abelian. So for non-abelian groups, actually, this Sambaria-Yamagami fusion ring doesn't have a corresponding fusion category, because you can't find absolutes. So it's kind of amazing that so we spent quite a lot of time building computer programs to do this better. And they can, for example, find that some of these other non-abelian fusion rings that I was talking about last week that look quite similar to these Sambaria-Yamagami things, but they have 2 extra elements or whatever. They actually have fusion categories, not just you can find all their symbols. You can find, for example, A solutions or whatever. Yeah, that's probably a good point to stop. So we're already 2 hours in, that's really enough. It's a lot for the question, though.
We'll go into another question. Last week you told us that you had with the 28,000 fusion rings. How many of those do you know the estimates for?
Yeah, so it's certainly limited. One of our big problems is that many of those 28,000 have quite high multiplicities.
Yes.
And this these tricks that we were using with the fixing gauge, they were great if you have multiplicity 1.
Yeah.
But for high multiplicity, this is all much more complicated because all you use combinations. They act on different Greek indices. Some of them are inverted. It becomes hard to think of ways to fix them by requiring things from the F.
So presumably the answer is a relatively small number of the
Well, it's interesting. Now we still have a fairly good number of ones that do have. Like there would be way more than modular tensor categories, for example. But very much smaller than 28,000. But also there are probably most of those 28,000 we couldn't say for sure that there is no. At least 15,000 or so we just don't know sure at the moment. But we have been working on doing these solutions for high multiplicities. And in particular, it should be relatively easy, I think, if you also require braiding. So if you also want to make braiding work, it's solved in hexagon, then it's much easier because then you can work with the transformations of the R symbols. They are simpler. And there I think we have really good hope to get to some pretty much higher multiplicities. The other thing that I didn't get around to saying, but which is interesting also, is that there are many things that you can calculate directly from the fusion rules. So for example, there's a structure called the S matrix, which is essentially you take this diagram where you two particles fighting with each other. So you think of this 4 particles because creation here, creation there, but then 2 of them braid and then they annihilate again. So you have this nice link diagram. And then there's a noble constant, but don't worry about that. And then this one has a label A here and a label B here, and this is called SAB, an important matrix, which also has something to do with transformations on the, modular transformations on the torus, and but don't have to worry about it.
It's a representation.
Yeah.
There's a T one as well.
There's a T as well, yeah. So there's also a T. If you make this diagram, then it's like T A times this word as well. TAA. So it's also a matrix, but these are the diagonal elements. So it turns out you can calculate these directly from the fusion coefficients, the fusion rules. You don't have to actually calculate the F and R symbols. So then, of course, you will find multiple solutions, and you don't necessarily know which ones will match which. You don't know what the rest of the topological information is, but if it turns out that you can't find any good solutions here from the fusion rules, then you already know that you can never find a full modular category either. So these tricks directly using the fusion rules allow us immediately to identify all the possible modular categories, and we don't find any that aren't. I don't think we find any that are unknown. There's a few that are not sort of standard what everybody mentions, but I think they're still known. So that's kind of interesting. You can do a lot of stuff directly from the fusion rules. It doesn't require all this machinery. But I promise to do something with categories. So I figured I'd show you what the information is.
I have 2 questions. You did mention, but I didn't really understand the answer.
Please ask again.
So the thing with the diagram that you had drawn there, and Brian asked, I didn't understand why you couldn't have 1 over crossing 1 under crossing.
You can have 1 over crossing 1 under crossing, but the point was that there's a consistency equation that comes from exchanging fusion or splitting with the braiding.
Uh-huh.
So it basically says that, okay, here there are two particles, and now I braid this over these two particles. But these two particles are, I know their global charge. This should really be the same as if I braid it over the global charge instead. So I take this thing and I move it over there. So this diagram. We require that since these histories are disrelated by this continuous reformation, they get the same amplitude. So that gives us the consistency with the relation of the R and get the Expo equation. But if you decide say that well, this one is going to be overclocking now, well now you actually can't move this to the other side of that line because it will just hit the line. This splitting will just get stuck on that line there.
But I can think of another diagram which seems consistent and gives me the same result. It would be a diagram that would combine B and C as right? Oh, yeah, it would be swapping A and B first, and then combining A and C. B and C.
You want to draw it?
So imagine the C line, which is overcrossing. If you draw it on the other side,
Where on this side?
yeah.
So we have something like
So that would be like I've swapped A and B, and then C and B together.
B goes over like this, and then it goes into B there, something like this. So it's
Yeah,
this.
so B, well, B and C are the ones that are going
together like
together.
that, and then A would be going over B here. And then it would be like this. Like this.
I know.
Yeah, this is also allowed. This is also in principle a consistency situation, yes. But you can show that it follows from the simpler one where you. So here I move this line over this crossing instead of moving it over over a vertex.
Yeah.
But if you remember, we can make this crossing disappear and make it into two vertices.
Yeah.
And then this is just moving over those two
Yeah.
vertices. So it's actually a more complicated one where you use the vertex thing twice.
Yeah, but it is consistent.
Yeah. Every deformation that you can think of, that's just deformation where you don't have to cut or glue and this gives you the same answer.
Okay.
Well, okay. Strictly speaking, there are some subtleties, but for first approximation, that's the correct answer.
Then my second question was here when you said you can write a fusion ring as a fusion category, the group is you say non-Abelian.
So here, this is a perfect fusion ring, regardless whether the group is Abelian or not. So we can take any finite group and it's a good fusion ring.
Okay.
But then I said at the end, okay, now here I give you the F symbols, which makes together with that information. Now it gives you the data of a fusion category.
Yes.
But that only works if the group is Abelian because there's a requirement. Sorry.
It would only work if the group is Abelian.
Yeah.
But it feels like it should only work if the group is not Abelian.
Why?
Because the group is Abelian. Then the order of applying the transformation doesn't matter.
Which one?
Well, why does it work with abelian?
So the point is that after you solve all the equations, you end up with these solutions, right? And then this you get to here regardless whether it's abelian or not. Like so, you can just solve the equations, not even knowing that it's a group even, pretty much. But then you have this requirement on this function chi here that it must be a symmetric bicharacter. That's still perfectly fine in principle. But now in the end, you say, and this matrix F sigma 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 here. So this is basically the transformation between where we have sigmas everywhere connected this way and this way. And the matrix element where it is G1 and this is G2. Right? So this is over F sigma 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 sigma. G1 G2, sum over G2. Okay. And then we say this thing is actually chi of G1 G2 or times some factor, which doesn't matter now. This is supposed to be an invertible or even unitary transformation. So because it's just a basis transformation. So this matrix better be a unitary matrix in these two. Now that's impossible if it's a non-Abelian group because we know these are the actual matrix elements.
Yeah.
So for every choice of G1, this is a one-dimensional representation of the group in G2. But they all have to be different one-dimensional representations, as otherwise some of the rows will be the same. And then it's not an invertible matrix.
All the elements have to be different.
So what I'm saying is that this matrix looks like chi E1. Let's put H1 here. Chi E1, H2, like that, and E2, H1, and E2, H2, etc. All the way down to chi G, as many elements as G, H1, like this. Okay. Now this matrix is supposed to be invertible. So all the rows are all different. Otherwise, two of the rows are the same. It won't be invertible. But that means that also for every choice of this first element, G1, G2, etc., this thing is a one-dimensional representation of the group in the second element. Because this property would do. If I choose G1, then the one-dimensional representation H2 in H. But an abelian group only has a small number of one-dimensional representations, smaller than the number of elements of the group. So that means that many of these are actually the same. So here are as many rows as the number of elements of the group, but you know, some of these representations have to be the same then.
In an abelian group.
In a non-abelian group.
No, why?
So in an abelian group, you have as many one-dimensional. Okay. So the number of elements of the group is the same as the sum over the irreducible representations I for G or the dimension of the irreducible representation squared. Is that the formula that's is familiar?
Yeah.
Okay. So now, if G is abelian, then the irreducible representation always G1. And then it just says, well, I have to have as many ones as the order of G, so that's the number of independent irreducible different representations. If it's non-abelian, well, then there is at least one pi with pi greater than 1. Otherwise, it could be non-abelian because the one-dimensional representations are automatically abelian. And then you can, and then the number of irreducible representations automatically smaller than the number of elements of G. Otherwise, this formula can't be true. Therefore, there are some rows here that are the same, and this matrix is not invertible. I know that was kind of elliptic. Any other questions?
Does this have any applications to high energy particle physics, or is it a bit too abstract or early for that?
So the applications tend to be to extremely low energy physics and extremely high energy physics. On the one hand, you have things like fractional quantum Hall systems where people think there are anions. These are quasi two-dimensional systems that are kept at temperatures of millikelvins. You're talking about quasi particles and moving them very slowly, etc. On the other hand, there's lots of applications to sort of string theory type things, which are of course extremely high energy. There are also and that's basically because string theory is heavily based on conformal field theory. And conformal field theory relates to this because conformal field theory it's usually in 1+1 dimension. So the string is of course a one-dimensional object, and then the extra dimension is time. But it's in an ambient space. So you can combine diffuse these one-dimensional things and these types of diagrams, which are similar to the fusion diagrams that we had. So now what happens is that if you imagine that you string the string more and more, so that these become points, then any excitations that are on the string become very energetic, relatively speaking, and become gapped. So they don't happen anymore. But you still left with this ground state of the string propagating through time this way. And then what I've been describing would be important for describing that, especially these amplitudes for this the lowest energy state of the string is being diffused and split. But you actually extend this to also take into account higher energy states, since that the whole structure gets an extra layer of complexity on top of this, but it's possible to do it. I don't know, intermediate is a bit.
Yeah, I mean, well,
Yeah.
There's an subject of non-Abelian symmetries, which is being in important role in QCD and in lots of field theories. We had two seminars already, one by Untitled and the other by Zohar.
Lucinov?
No, he's
a different Zohar. Okay.
Yeah.
But yeah. Yeah, these are systems where you're at a very specific, you go towards a critical point of the system where there's you're sort of a very enhanced symmetry. So you have two phases coming together, they both have their own symmetries. Then you go to a critical point where you switch from one phase to the other, but somehow you manage to retain all the symmetry from both phases. And it gives you all this topological kind of space to play with, and whenever that happens, these kind of ideas become important again. I think that's the very naive summary. But
it was sort of Komaratsky, people wrote QCD tree and these other sort of things. But also I think they've been shown to play a role in the critical point in the two-dimensionalizing model, or just not even the critical point. The two-dimensionalizing model where you couple the system which is dual from the defect line, and the defect line is over on these elements.
Yeah, a lot of these things are kind of more universal than you might think. So it's difficult to say immediately, oh, this will apply to some very specific physical system, but there are lots of things where you find these ideas back. So I mean, a lot of this is, all these diagrams I'm drawing are very similar to Feynman diagrams. So now, of course, if you want to actually calculate the values of Feynman diagrams, you usually have to do lots of integrals over momentum space. There's complicated stuff. But if you want to find out things that are about these kind of diagrams that are just fixed by some extended symmetry or something where it doesn't depend on those kind of details, very often you end up with these types of arguments again, where you say, oh, well, we can recouple the diagram. So instead of having the electron split off the photon over here, and then this photon goes with the other electron, sense. You know, with this kind of thing. We go from here to a picture like this.
Classic symmetry.
Yeah, exactly. And for whatever reason, we have some symmetry that says that these are simply related, should we give the same answer, or we have to sum up all these diagrams, so therefore it doesn't matter, or we can change the basis in a way where it doesn't matter what we use as our initial as our description. Then you straight away think, oh wait, that's very similar to those F moves.
Yeah.
Now you may have some differences to what I just said. So maybe instead of having only finitely many different charges, you have infinitely many different charges, or even continuous charges. But a lot of the ideas are the same. So you will probably end up with some Pentagon type equation again. And, so a lot of these ideas basically come back in lots of branches of physics. Just in this specific detail, most likely, yeah. If in your application it would be something different, slightly different, but I think it's nevertheless a useful set of ideas for many physicists to know about. That's my that's my opinion anyway.
So how did you get interested in fusion rings? Do you start from the top down or whatever?
So originally this was about 2006 or 7. I was working on quantum Hall systems, and people were trying to think about interferometry quantum Hall systems with anions. And we had a specific question there about there were anions, and they were supposed to have Fibonacci times 3 fusion rules. So at this time I would have already known about fusion rules and conformal field theory. In the quantum Hall effect, all this stuff kind of comes naturally rolling out because you need to. But this kind of started us off thinking, because we knew the fusion rules had this this structure, but we didn't know the actual fusion category, the actual F symbols, and etc., which were important for calculating what would happen in the interferometer. But they would also split into an ion product like that. And in order to know, we would have to solve the Pentagon equations, because it wasn't clear what the correct answer was. So we this is not so easy, because this is already a theory of 6 different types of particles. So the Pentagon equations, they have these F symbols, and there's 6 possibilities for all of the labels, and it was just about possible perhaps to do it by hand, but we got to maybe 3/4 of the way through, and then we said, well, the chances that we made a mistake somewhere now are just too big. So I wrote a computer program to solve it. And then since then, it seems like just about nobody else has been able to write a better computer program until we finally got together and said, okay, let's like make it so other people can use it. So that's where we are now. So
What is the program called?
So the original one was not called anything. It was just a big Mathematica notebook that was in my computer. And the one that we have now does have a name, but we haven't really put it out there yet. But I can anyway send you the
It would be very useful.
Yeah.
Obviously, we have a lot of applications for particle physics.
Yeah, hopefully.
Yeah.
They have a big website.
Sorry,
You have a big
there's a
website.
big website with all the fusion rules that we not even all, like a small part of the fusion rules we found explicitly indicates. So it's called Anion Wiki, and we do plan to make all this information available there. But you know how it is, like you find interesting news so fast, and then you can put it on the on the website. But there is some interesting stuff there already, and we'll make sure that eventually you can download all the software from there also.
Yeah.
Right.
I think I've got a couple of cards here.
Yeah, this is probably a good idea. Yeah.
There is a mini course.
Yeah. Sorry about this.
Very, very good. Yeah. I love the way you told the story.
Oh, thank you.
It really did feel like, oh, I want to see what happens next.
Yeah. Good. Yeah. Thank you for seeing something.
Yeah.
Thank you.
That's long becoming. Yeah.
I was wondering, what happens with the
So this Friday is not.
No.
yes.